Hello there, and welcome to Sleepy Science Vault. Somewhere above you, right now, there is a stretch of space so vast and so dark that our minds struggle to hold its true shape, and for most of human history, we called that stretch nothing. Empty. Void. A black backdrop against which the real business of the universe, stars, planets, galaxies, seemed to unfold. It felt obvious. Space between things must be the absence of things. And yet, the deeper physics has looked into that darkness, the less empty it has turned out to be. This is where our journey begins tonight, not among the stars themselves, but in the spaces between them. In the quiet, overlooked fabric that holds everything else in place. We are going to spend these coming hours exploring what scientists actually mean when they use a word as simple and as deceptive as vacuum. It is a word that sounds like an ending. In truth, it is closer to a beginning. Let's start with the plainest fact, the one that quietly undoes a lifetime of casual assumption. Space is not truly empty. Even in the most desolate regions astronomers can point a telescope toward, the so-called vacuum is still populated. It carries thin traces of gas, drifting specks of cosmic dust, and radiation moving silently through the dark. It carries gravity, reaching out from every mass in the universe, weaving distant bodies together in an invisible net. It carries electric and magnetic fields, rippling outward from stars and planets alike. It carries cosmic rays, high-energy particles born in the violent hearts of exploding stars, crossing unimaginable distances to pass through regions we once thought had nothing in them at all. And that is only what we can detect directly. Hidden within that same darkness is dark matter, a substance we cannot see, cannot touch, and cannot yet fully explain, known mostly by the gravitational fingerprints it leaves on galaxies. Woven through it as well as dark energy, the mysterious pressure that appears to be pushing the universe to expand faster with each passing moment. Gas, dust, radiation, gravity, fields, particles. Two forms of matter and energy we still barely understand. All of it, sitting quietly inside what we once dismissed as emptiness. It's worth pausing on that thought for a moment, because it changes the entire character of the universe. If space were truly nothing, then existence would consist of isolated objects, scattered across a void with no relationship to one another. But if space itself is filled with structure, then everything is connected by way of the medium it moves through. The stars are not floating in nothingness. They are floating in something. Something subtle, something faint, but something real. For a long time, this idea sat mostly in the realm of philosophy. Ancient thinkers debated whether a true void could even exist. Aristotle, one of the most influential minds of the ancient world, rejected the notion outright. He believed nature abhorred a vacuum, that empty space was, in a sense, physically impossible, because the universe would always rush to fill any gap the moment it appeared. For centuries, his view shaped how people understood the world around them. Nothingness, in his eyes, simply had no place in nature. It would take many generations, and a great deal of careful, patient science, before that ancient assumption began to change. As physics matured, our definitions of empty kept shifting beneath our feet. Each time scientists thought they had found true nothingness, a new layer of structure would reveal itself, hiding just beneath the surface of what could be measured with the tools of the time. The story of the vacuum, in many ways, is the story of physics itself slowly learning how much is hiding inside an apparent absence. This brings us to one of the more elegant ideas in modern physics, the notion that the vacuum is no longer treated purely as an old philosophical nothingness. It is treated as an active physical system. Not a stage on which the universe performs, but a participant in the performance itself. And this shift in thinking was not born from speculation. It was born from measurement. From observable, repeatable consequences that could only be explained if the vacuum itself had physical properties. Consider that for a moment. A region with no particles in the traditional sense, no solid matter, no obvious substance, and yet it can produce force. It can shift the energy of a nearby object. It can leave traces in delicate laboratory experiments, detectable by instruments sensitive enough to notice a whisper of physical influence where classical thinking said there should be none at all. This is the paradox at the very heart of tonight's exploration. The vacuum seems, on its surface, like the emptiest possible expression of nothing. And yet it produces effects that ripple outward into the observable world. Physics has come to treat empty space almost like a fabric, though not a fabric in the literal sense of woven threads. Rather, a fabric of fields. Fields that exist everywhere, quietly present even where no particles seem to be. An electric field can exist in a region with no charges nearby. A magnetic field can linger in a stretch of space with no visible source close at hand. These fields are not simply the leftover trace of distant objects. In many interpretations of modern physics, the fields themselves are considered the more fundamental reality, and particles are treated as small disturbances, ripples, moving through this deeper underlying structure. Under this view, space is never a blank canvas. It always carries the quiet potential of these fields, present and waiting, even in their most undisturbed state. It's easy to see now why the vacuum has become, for many physicists, one of the most paradoxical and fascinating subjects in the entire field. Something that appears, in every intuitive sense, like nothing at all, and yet produces effects at nearly every scale of existence. On the smallest scales imaginable, inside the strange mathematics of quantum theory, the vacuum shows behavior that seems almost restless. On the largest scales conceivable, across the vast unfolding structure of the cosmos, the vacuum appears connected to the very expansion of the universe itself. A single concept, stretching from the tiniest imaginable point to the grandest imaginable whole. And here we arrive at something important to hold on to as we continue this journey. The meaning of the word empty depends entirely on which scientific framework is doing the describing. In the older, classical picture of physics, developed long before the 20th century's quantum revolution, a vacuum truly could be described as empty. No particles. No matter. A clean, calm nothing, consistent with what intuition tells us. But once physics moved into the quantum realm, once scientists began exploring the tiniest, most fundamental layers of reality, that same vacuum stopped behaving so simply. quantum theory revealed that even a region with no particles present still carries measurable structure, still carries activity, still carries a kind of underlying hum that never fully goes silent. This is sometimes described, almost poetically, in physics discussions as nothing's plenty. Empty, in one sense. Rich beyond expectation, in another. A vacuum that is simultaneously as empty as our intuition demands, and as active as our most precise instruments can detect. It's a strange kind of harmony, isn't it? Two seemingly contradictory truths, sitting comfortably inside the same phrase. Nothing, and yet, plenty. This is not a flaw in our understanding. It is, in many ways, one of the more beautiful aspects of how physics has grown to describe reality. Different frameworks reveal different layers of truth, each valid within its own boundaries, each offering a different vantage point on the same underlying mystery. And this mystery is far from a settled or minor curiosity. Many physicists consider the vacuum to be one of the most important missing pieces in our overall understanding of nature. It sits at a kind of crossroads, one path leading toward quantum theory, which describes the smallest scales of existence with extraordinary precision, and another path leading toward cosmology, which describes the largest scales of existence, the shape and history and future of the universe as a whole. The vacuum may be the bridge that eventually allows these two very different frameworks to be understood as a single, unified description of reality. That bridge has not yet been fully built. But its outline is beginning to appear, quietly, patiently, in the accumulated evidence of decades of careful research. So when we return, in the segment ahead, to explore this vacuum more closely, we will begin looking at what modern quantum theory actually claims is happening within it. What kind of activity fills a space with no particles? What kind of energy hides inside apparent nothingness? For now, let this first idea settle gently into the quiet of your thoughts, that the darkness above you, and the darkness all around every corner of the universe, is not truly dark in the way we once assumed. It is alive with structure. Alive with fields. Alive with a subtle, invisible richness that scientists are still, even now, learning how to fully describe. And it's into that richness that will continue drifting, deeper and slower, as the next set of facts begins to unfold. Long before physics had the tools to measure anything as delicate as empty space, philosophy was already circling the same question. And one voice in particular stands out from that earlier era. René Descartes, writing in the 17th century, could not accept the idea of true nothingness existing anywhere in the universe. To him, the very notion of a region containing absolutely nothing seemed logically impossible. If space existed, he reasoned, it had to be filled with something, some kind of substance, extending continuously from one object to the next. He proposed an invisible medium filling all of space, a subtle material presence that made emptiness itself impossible in principle. It was, in many ways, an early philosophical ancestor of ideas that physics would return to again and again in the centuries that followed. Long before anyone had instruments capable of testing such a claim, the intuition was already there, that emptiness might be an illusion, and that something unseen might be quietly holding the universe together. That intuition did not fade with time. It resurfaced in a new form during the 1800s, when physicists were grappling with a puzzle of their own. Light, they had come to understand, behaved like a wave. And waves, as far as anyone knew at the time, needed something to wave through. Sound needs air. Ripples need water. So surely, light needed some kind of medium as well, something to carry its oscillations across the vast distances between stars and across the shorter distance between the sun and our own eyes. This reasoning gave rise to one of the most famous ideas in the history of physics. Scientists proposed the existence of a substance they called the luminiferous ether, an invisible, weightless material believed to fill all of space, silently carrying light the way water carries a wave toward the shore. For decades, this idea held real scientific weight. Careful experiments were designed to detect this ether, to measure Earth's motion through it, to finally prove that this unseen medium truly existed. But nature, as it so often does, had a quieter and more elegant answer waiting. Those experiments, performed with increasing precision, kept returning a result no one expected. No ether could be detected. No matter how carefully scientists searched, the medium simply would not reveal itself. And then, in the early years of the 20th century, a young physicist named Albert Einstein offered an explanation that reshaped the entire conversation. Through his theory of special relativity, Einstein showed that light does not require a stationary medium to travel through at all. Its behavior could be fully explained without any ether whatsoever. The idea, so carefully constructed and so widely believed, quietly dissolved, not through argument, but through a deeper and more complete understanding of how light and space actually behave. It was a profound moment in the history of science. An idea that had felt almost obvious for 100 years turned out to be unnecessary. And yet, this did not mean that space returned to being simple, static, and truly empty. If anything, the story that followed made space even more remarkable. A decade after special relativity, Einstein returned to the nature of space itself with an even larger and more ambitious theory, general relativity. This time, instead of removing structure from space, his equations revealed a new and unexpected kind of structure hiding within it. Space, it turned out, was not merely a fixed backdrop against which events occurred. It could bend. It could stretch. It could ripple in response to the movement of extremely massive objects, sending waves rolling outward across unimaginable distances, much like a stone dropped into still water sends ripples spreading across its surface. These ripples came to be known as gravitational waves, and though Einstein predicted them mathematically many decades ago, it would take until the 21st century before scientists finally detected them directly, using instruments sensitive enough to notice a stretch and squeeze in space itself, smaller than the width of a single atomic nucleus. It's a remarkable thought to sit with for a moment. Space, once imagined as a fixed and passive stage, revealed itself instead to be dynamic, capable of motion, capable of carrying energy, capable of physically responding to the drama unfolding within it. The ether had been removed from physics. But something far stranger, and far more real, had taken its place. With this foundation in mind, it becomes useful to slow down and consider how physics actually defines the word vacuum in careful, technical terms. A vacuum, in the language of physics, refers to a region containing no matter, or, in a more practical sense, a region where the pressure is so extraordinarily low that any particles present have no significant effect on whatever processes are occurring there. This distinction matters a great deal. It tells us that a vacuum is rarely absolute in the strictest sense. It is, more often, a matter of degree, a spectrum stretching from mostly empty, to nearly empty, to as close to true emptiness as the universe seems willing to allow. And when we look outward, into the depths of space itself, we find that even the universe's grandest emptiness fits this description of nearly rather than completely. Space is best described as an almost perfect vacuum. Even in the most remote regions imaginable, drifting far beyond the edges of galaxies, matter has never fully vanished. It thins. It scatters. It becomes faint beyond ordinary imagination. But it does not disappear entirely. Consider the space that stretches between galaxies, vast, dark, and largely silent. In these regions, scientists estimate there can be less than one atom in every cubic meter of space. Try, for a moment, to hold that number in your mind. A cubic meter is roughly the size of a small crate, easily fitting in the corner of a quiet room. And within that entire volume, drifting through intergalactic space, there may be less than a single atom to be found. And still, physics insists, that is not the same as nothing. Even at that staggering level of thinness, matter remains present. Emptiness, even at its most extreme, still carries a faint trace of substance. It is worth remembering, too, that a vacuum is not only something we observe out among the stars. It is something we can also create here on Earth, using careful and deliberate engineering. Scientists and engineers produce vacuums inside laboratories, inside sealed chambers, inside countless pieces of everyday technology, by removing air from an enclosed space. This can be done using a vacuum pump, a device built specifically to draw gas molecules out of a container until the pressure inside drops far below that of the surrounding atmosphere. In other cases, engineers achieve similar results by lowering pressure gradually through the careful movement of fluid, coaxing gas away from a region step by step, until what remains behind is about as close to true nothingness as human technology can manage. Because vacuums are created and studied so precisely, physics does not describe them the way it might describe a substance, with a name or a chemical formula. Instead, a vacuum is measured using units of pressure, specifically a unit known as the Pascal. This might feel like a small, technical detail, but it reveals something meaningful about how physics actually understands emptiness. A vacuum is not treated as a separate kind of stuff. It is treated as a condition. A state of very low pressure, existing somewhere along a long and continuous scale, rather than a distinct material with properties all its own. And this brings us, gently, back to where our journey in this segment began, to the deeper, more modern understanding physics now holds of the vacuum. In current physics, particularly in the quantum picture of reality, a vacuum is often defined as a state containing no particles. No solid matter drifting through it. No detectable specks of dust or gas contributing to its structure. And yet, even in this most careful and precise definition, one crucial detail remains. A vacuum, even when entirely free of particles, can still contain fields. It can still contain fluctuations, subtle, quiet stirrings within those fields, appearing and vanishing in ways that classical intuition would never expect. This is the quiet thread we will follow further as our exploration continues. A vacuum with no particles at all, and yet, not truly still. Not truly silent. Somewhere beneath the absence of matter, something else remains, something we have only briefly touched upon so far, waiting patiently for us to look closer. And it's there, in that deeper layer of quantum stillness and quantum motion, that our next set of facts will gently carry us. Let's stay in this quiet layer of reality for a while longer, because it is here, in the language of quantum field theory, that the true character of the vacuum begins to reveal itself most clearly. When physicists speak of a vacuum in this deeper framework, they are not describing a state where fields simply switch off, leaving nothing behind. Instead, the vacuum is understood as the lowest energy state that those fields can occupy. Not an absence of fields. Not a gap where reality forgets to exist. Simply the calmest, quietest configuration those fields can settle into, while still remaining fully present. This distinction matters more than it might first appear. In everyday language, we tend to imagine lowest energy as being close to nothing at all. But in the mathematics of modern physics, low energy is not the same as no reality. The vacuum state is often described as the ground state of the fields that fill our universe, the floor beneath which nothing lower can be found, but a floor that still has structure, still has substance, still has a kind of quiet architecture holding it together. It is less like an empty room and more like a lake at its stillest possible moment. The water has not vanished. It has simply reached the calmest form it is capable of taking. And what fills this ground state is not a single, simple thing. Quantum field theory tells us that even in a vacuum, even when no particles are present at all, there are still fields quietly occupying that space. Light fields, connected to the electromagnetic force that gives us everything from sunlight to radio waves. Matter fields, connected to the particles that build atoms, and molecules, and eventually stars and planets and every living thing. These fields do not require particles to exist. They are always there, spread across the whole of space, whether or not anything is currently disturbing their surface. This brings us to one of the more quietly astonishing ideas to emerge from 20th century physics, the reversal of how we think about particles altogether. For a long time, particles were imagined the way the word itself suggests. Tiny balls. Small, solid, indivisible bits of matter, bouncing through space like miniature stones. But quantum field theory offers a very different picture. Particles are not treated as fundamental little balls at all. They are treated as excitations, ripples, disturbances, stirring in a field that fills all of space, including the space we would ordinarily call empty. Picture, for a moment, the surface of still water. A ripple moving across that surface is not a separate object added to the water. It is simply the water itself, briefly disturbed, briefly taking on a different shape before settling again. A particle, in this framework, is something similar. Not a separate thing placed into space. but a temporary shape taken on by a field that was already there. Once this idea settles in, it changes the entire order of what we consider fundamental. For most of scientific history, matter felt like the foundation of reality, with fields treated as a kind of secondary description, useful but somehow less real than the solid particles they were meant to explain. Quantum field theory quietly reverses that hierarchy. The field is the deeper reality. It exists everywhere, continuously, filling every corner of space whether disturbed or still. Particles are what we notice when that underlying field briefly rises into an excited state. The dance we can see, performed upon a stage we mostly cannot. It's worth pausing here to consider just how far this reshapes our picture of what removing everything would actually mean. Imagine, for a moment, a thought experiment. Suppose you could take a region of space and strip away every last trace of ordinary matter. Every atom. Every stray particle of gas or dust. Every scrap of familiar material substance. Would what remained finally qualify as true, absolute nothingness? According to modern physics, the answer is no. Even after every particle has been removed, a physical vacuum would still retain several deep and fundamental properties. It would still carry vacuum energy, an underlying baseline of energy woven into the fabric of empty space itself. It would still contain the Higgs field, quietly filling the space around it. And it would still be shaped by space-time curvature, the same gentle bending of space and time that general relativity revealed nearly a century ago. Strip away everything ordinary, and something extraordinary still remains behind. That mention of the Higgs field deserves a moment of its own, because it plays a role in our universe that is easy to overlook, yet profound once understood. The Higgs field is believed to fill all of space, quietly, invisibly, the same way the fields we discussed a few moments ago fill it as well. And this particular field carries a very specific responsibility. It plays a central role in giving fundamental particles their mass. Without this field's presence, many of the particles that make up matter as we know it would behave as though they had no mass at all, moving endlessly at the speed of light, unable to slow down long enough to form atoms, or stars, or anything resembling the physical world around us. The very fact that matter has weight, that it can gather and cling together and build something as solid as a mountain or as delicate as a snowflake, ties back to this quiet, space-filling field, always present, always active, even in the stillest, most apparently empty regions of the universe. The Higgs field is not alone in shaping how the vacuum behaves. Other forces of nature are tied to it as well. Consider the particles known as the W and Z bosons, responsible for carrying what physicists call the weak force, one of the fundamental forces shaping how particles interact at the smallest scales. In modern particle physics, these force carriers are deeply connected to the properties of the vacuum itself. The way they behave, the mass they carry, the influence they exert, all of it is shaped by the underlying structure of empty space, rather than existing independently of it. Even the forces that govern the tiniest building blocks of matter are, in a very real sense, products of the vacuum's own quiet architecture. And now we arrive at perhaps the strangest and most enchanting layer of this whole exploration, the idea that empty space is never fully at rest. Quantum mechanics suggests that a vacuum, even in its most undisturbed state, is filled with constant fluctuations. Tiny, fleeting stirrings, rising and falling within the fields that occupy space. Among these fluctuations are what physicists call virtual particles, particles that briefly appear, existing for the smallest imaginable sliver of time, before disappearing again, often paired together as a particle and its corresponding antiparticle, born together and gone together, leaving barely a trace of their passage. This behavior is made possible by one of the more famous ideas in all of quantum theory, the uncertainty principle. In the strange mathematics of the quantum world, energy and time are connected in a delicate balance. The uncertainty principle allows short-lived energy fluctuations to occur in the vacuum, so long as they remain brief enough to stay hidden beneath the threshold of what could otherwise be measured directly. For an instant almost too small to imagine, energy can seem to appear from nowhere, forming a pair of particles, and then, just as quickly, it vanishes again, as though the universe briefly considered a possibility, and then quietly let it go. It's a strange and beautiful image to hold in your mind as you rest here in the dark. Space, appearing calm and silent on the surface, and yet, underneath that stillness, endlessly whispering with these brief, fleeting appearances and disappearances. Particles rising for a heartbeat's fraction of a moment, and dissolving again into the quiet hum of the fields from which they came. Not empty in the way we once imagined. Not silent in the way stillness usually suggests. But alive with a constant, gentle trembling, a vacuum that never quite stops moving, even in its most peaceful and undisturbed form. As we continue forward from here, we'll look more closely at what these virtual particles actually do, how their brief, flickering presence can leave real, measurable consequences in the world around us, and how something so fleeting and so small could possibly matter to the much larger universe unfolding above you. We left off with a strange kind of trembling, hidden just beneath the calm surface of empty space. Now, let's slow down and look more closely at exactly what that trembling involves, because this is where the vacuum stops being an abstract idea, and starts becoming something with real, measurable consequences. At the heart of this trembling lies the same uncertainty principle we touched on a moment ago. It permits vacuum energy to fluctuate, but only for the briefest imaginable stretches of time. This is not a loophole in nature's rules. It is, in a sense, a built-in feature of how reality operates at its smallest scale. Energy is allowed to borrow itself briefly from the surrounding vacuum, so long as it returns that borrowed energy before the universe, so to speak, notices anything has changed. This principle forms the very foundation of what physicists call vacuum fluctuation effects, small, fleeting departures from stillness that ripple through empty space, over and over, endlessly, in every corner of the universe. These fluctuations are most often described in terms of particle pairs. Specifically, the temporary appearance of a particle alongside its antiparticle, a mirror image of itself, carrying opposite charge, born into existence together and vanishing together almost as quickly. One of the more familiar examples in physics is the electron and its antiparticle, known as the positron. For an instant far too brief to observe directly, such a pair can flicker into being, drawing their fleeting existence from the underlying energy of the vacuum itself, before recombining and dissolving back into the quiet hum from which they emerged. This idea did not appear all at once. It grew slowly, through decades of careful theoretical work, as physicists began connecting a few different threads of understanding. One of those threads reached all the way back to one of the most famous equations in the history of science. Einstein's simple, elegant relationship between energy and mass, often written as E equals mc squared. This equation tells us that energy and mass are, in a deep sense, interchangeable, two expressions of the same underlying quantity, depending on how it happens to be arranged. Early explorations of vacuum physics drew on this relationship directly, linking it to the strange behavior allowed by quantum uncertainty. If energy could briefly fluctuate within the vacuum, and if energy could be converted into mass, then perhaps that fluctuation could, for an instant, take the form of matter itself, a fleeting particle, born from nothing more than a momentary imbalance in the quiet field of empty space. It's a delicate, almost fragile idea to hold in your mind. And yet, it is far from purely theoretical. These fluctuations leave behind real, observable fingerprints in the physical world. Consider the electromagnetic field, the same field responsible for light, for radio waves, for the invisible signals that connect much of modern life. Even in a region with no particles present at all, this field can fluctuate just enough to produce consequences that scientists are able to measure directly, using careful and sensitive instruments. Empty space, in other words, is not merely a passive backdrop. It is quietly active, in ways precise enough to leave a mark on the world we can observe. One of the clearest examples of this activity involves atoms, and the light they emit. Imagine an atom that has been excited, its electron nudged up into a higher energy level, carrying a little more energy than it would in its natural, resting state. Eventually, that electron settles back down, releasing its extra energy in the form of light. For a long time, this process seemed almost automatic, a natural consequence of the atoms simply returning to balance. But vacuum fluctuations offer a deeper explanation for why this happens on its own, spontaneously, without any outside influence pushing it along. The fluctuating vacuum, with its constant flickering of underlying fields, gently nudges the excited atom, encouraging it to release its light even in the complete absence of any external trigger. This phenomenon is known as spontaneous emission, and it stands as one of the more elegant, practical demonstrations that the vacuum is not merely empty, but quietly influential, shaping the behavior of matter even when nothing else appears to be present. This becomes a wonderfully useful example, because it grounds such an abstract idea in something concrete and observable. The vacuum, this strange and paradoxical concept we have been circling throughout our exploration tonight, turns out to be a direct source of practical, measurable effects. It shapes how atoms behave. It influences how and when they release light into the world around them. Something we might once have described as pure emptiness is, in fact, quietly steering the physical behavior of matter, atom by atom, moment by moment, all across the universe. There is another subtle effect tied to this same underlying activity, one that involves not light, but electric charge itself. Physicists refer to it as vacuum polarization. Here, the fleeting particle-antiparticle pairs we discussed earlier play a quiet but meaningful role. As these virtual pairs flicker briefly into existence around a charged particle, they arrange themselves in a very particular way. The particle carrying an opposite charge tends to drift slightly closer to the original charge, while the particle carrying the same charge tends to drift slightly further away. This subtle rearrangement creates a gentle screening effect, slightly softening how strongly that charge is felt by anything nearby. It is a small effect, but a real one, arising directly from the restless, flickering nature of the vacuum surrounding every charged particle in existence. This same flickering activity leaves its fingerprint elsewhere too, in a phenomenon known as the Lamb shift. Within an atom, the energy levels available to an electron are shaped, at an extraordinarily precise level, by its ongoing interaction with the fluctuations of the surrounding vacuum. This interaction produces a tiny, measurable shift in those energy levels, a shift so small it required extraordinarily delicate experiments to detect, yet one that matched theoretical predictions with remarkable precision once it was finally observed. The Lamb shift stands as a quiet, elegant confirmation that the vacuum's fluctuations are not simply a mathematical convenience invented to make the equations work. They are a real, physical presence, subtly reshaping the behavior of atoms in ways that can be measured, verified, and trusted. And then there is perhaps the most striking demonstration of all, an effect that shows the vacuum can do something almost impossible to imagine from a classical point of view. It can exert a force. Physicists call this the Casimir effect, and it involves two ordinary metal plates, placed extremely close together, with nothing but vacuum in between them. According to older, classical intuition, two uncharged plates like these should feel no attraction toward one another at all. There is no material connecting them. No obvious force reaching across the gap. And yet, when physicists perform this experiment with sufficient precision, the plates draw slightly closer together, pulled by a force that has no explanation in classical physics whatsoever. The explanation lies once again in those quiet vacuum fluctuations we've been following throughout tonight's journey. Outside the narrow gap between the plates, the vacuum is free to fluctuate across an unrestricted range of possibilities, generating its usual, constant hum of fleeting activity. But inside the gap, between the two closely spaced plates, only certain patterns of fluctuation are allowed to exist, restricted by the narrow boundary the plates create. This difference, subtle as it sounds, produces a very real imbalance in the underlying vacuum energy on either side of the plates. And that imbalance manifests as a gentle, measurable pressure, pushing the plates ever so slightly together. The Casimir effect has become one of the clearest demonstrations available to modern science that the vacuum can exert real, physical pressure between objects. Not a philosophical curiosity confined to complex equations. A direct, measurable force, arising from nothing more than the quiet structure of empty space itself, confirmed again and again under careful laboratory conditions. It stands as a kind of quiet proof, gathered patiently over decades of research, that everything we have been exploring together tonight, the fluctuations, the fields, the fleeting particles rising and falling in the dark, is not simply an elegant story told by physicists to make sense of strange mathematics. It is a real and active feature of the universe, leaving behind fingerprints subtle enough to require our most careful instruments, and yet undeniable once they are found. As we drift onward from here, carrying this quiet image of two plates, drawn gently together by nothing more than the restless energy of empty space, we'll begin turning our attention toward even larger questions: how this same vacuum energy might ripple outward across the whole of the cosmos, and what role it may be playing in the shape and the fate of the universe entwined around us. We ended the last stretch of our journey with the Casimir effect, two plates, drawn quietly together by nothing more than the underlying structure of empty space. It's a remarkable piece of evidence on its own. But it is far from the only way scientists have found to reach into the vacuum and confirm, with careful precision, that something real is happening there. Let's spend this next stretch of time exploring just how far that confirmation has gone, and how researchers have moved, gradually, from indirect hints towards something closer to direct observation. For much of the history of this field, vacuum fluctuations were understood primarily through their consequences rather than through any direct glimpse of the fluctuations themselves. This remains true in many cases even today. Vacuum fluctuations can be measured indirectly, through subtle shifts in atomic behavior, through tiny forces between objects, through small but consistent departures from what classical physics alone would predict. And yet, in certain carefully designed experiments, physicists have managed to move a step further, capturing effects that come remarkably close to a direct measurement of the fluctuations themselves, rather than simply their aftermath. One of the more elegant approaches to this challenge has involved light. Rather than attempting to observe the fluctuations directly, in some sense an almost impossible task given how brief and subtle they are, researchers have instead studied how those fluctuations quietly influence a beam of light passing nearby. Light, in this context, becomes something like a very delicate messenger, carrying, within the tiny variations of its own behavior, a faint record of the vacuum's restless activity. By studying these subtle variations with extraordinary care, scientists have been able to characterize vacuum fluctuations without ever needing to observe them directly, relying instead on the fingerprints they leave behind in the light that passes through their presence. But the story does not end with indirect observation alone. In more recent years, some physicists have gone further still, reporting what they describe as direct measurements of vacuum electric field fluctuations. This marks a meaningful shift in how concretely this once purely theoretical idea can now be grounded in experimental evidence. Rather than inferring the vacuum's activity purely from its downstream effects, these experiments aim to capture something closer to the fluctuations themselves, as they happen, within carefully controlled laboratory conditions. The method behind these measurements is worth pausing on, because it reflects the same quiet elegance that runs through so much of this field. Researchers used changes in the polarization of a probe light beam, a subtle rotation in the orientation of the light's oscillation, to detect tiny variations tied directly to the vacuum's underlying activity. Polarization, in this context, becomes an extraordinarily sensitive instrument. As the light beam passes through a region influenced by vacuum fluctuations, its polarization shifts in small, measurable ways, offering a kind of quiet signature of the fluctuations rippling through the space it traveled through. It is a beautifully indirect kind of directness, using light as an intermediary, sensitive enough to register echoes of a vacuum's restless quiet trembling. This connection between light and the vacuum runs deeper still, extending into how light behaves as it passes through certain physical materials. Some experiments have shown that the vacuum can influence how light moves inside a material crystal, subtly shaping the signals that researchers observe in their instruments. It's a striking demonstration of just how far this idea reaches. What began as a purely conceptual notion, that so-called nothingness could carry real physical structure, has grown into something concrete enough to leave its mark on real, reproducible experimental signals, gathered under carefully controlled laboratory conditions, again and again. And this raises a fascinating question, one that naturally follows once we accept that the vacuum has measurable structure at all. If the vacuum can influence experiments in these small, subtle ways, could scientists ever go further? Could they actively reach into that structure and change it? As it turns out, the answer is yes. Researchers have created conditions in which the vacuum state itself becomes strongly altered, demonstrating that the vacuum is not simply a fixed, unchangeable backdrop, but something that can, under the right circumstances, be manipulated experimentally. This achievement rests on an idea that sounds almost paradoxical at first. Vacuum fluctuations, as we discussed earlier, occur on extraordinarily short timescales, flickering into and out of existence faster than almost anything else in physics. To meaningfully disturb this process, researchers needed a way to intervene even faster than the vacuum's own natural rhythm. And remarkably, they found one. By switching certain interactions within engineered structures faster than the vacuum's natural fluctuation timescale, physicists managed to catch the vacuum, in a sense, off guard, altering its usual behavior before it had time to settle back into its familiar, undisturbed state. The results of this kind of experiment are genuinely striking. When researchers disturbed the vacuum in this way, the collapsing vacuum state produced something that can only be described, quite fittingly, as a kind of ringing, a measurable oscillation appearing in the emitted electromagnetic field, as though the vacuum itself had been struck gently, like a bell, and left to vibrate briefly before settling back into stillness. This ringing offers some of the clearest evidence yet that the vacuum is not merely a static condition sitting quietly in the background of the universe. It is capable of dynamic behavior, responding, adjusting, and briefly resonating, much like any other physical system that has been disturbed from its natural resting state. To help make sense of behavior this delicate and this abstract, physicists have often turned to more familiar systems here on Earth, using them as useful analogies for what might be happening within the vacuum itself. Superconductors, along with other carefully engineered solid-state systems, are sometimes studied for exactly this purpose. These materials, cooled to extraordinarily low temperatures, exhibit their own version of a ground state, a lowest possible energy configuration, not unlike the vacuum's own ground state within quantum field theory. By studying how these solid-state systems behave, how their own quiet, underlying structure responds to careful disturbance, researchers gain a valuable working model for understanding aspects of vacuum behavior that remain difficult to observe directly, out in the vast open reaches of space. This naturally brings us to a fascinating and somewhat counterintuitive idea, one well worth sitting with quietly for a moment. It would be reasonable to assume that if you cooled a system down far enough, all the way to the coldest possible temperature the universe allows, you might finally arrive at something resembling true, absolute stillness. A point where all activity, all fluctuation, all restless quantum trembling, simply comes to an end. But this is not what physics finds. The vacuum's baseline energy persists even at absolute zero. Cooling a system down as far as physically possible does not remove its underlying vacuum behavior. Even in that coldest, quietest, most theoretically motionless state imaginable, the ground state fluctuations we've been exploring throughout tonight's journey remain quietly present, woven into the very structure of that stillness itself. It's a gentle reminder of something we touched on earlier, and one worth carrying forward as our journey continues. Nothingness, in the language of modern physics, is rarely as simple as it first appears. Cool a system down as far as nature allows, and something remains. Strip away every particle you can find, and something remains. Search for a truly static, motionless corner of the universe, and even there, a quiet trembling persists, beneath the surface, patient and unyielding. The vacuum, again and again throughout this exploration, reveals itself not as an absence, but as a foundation. Quiet, yes. Subtle, certainly. But never entirely still. As we move onward from here, we'll begin turning our attention to how this same quiet foundation connects to the very structure and history of the universe itself, how this vacuum energy, so delicately measured in laboratories here on Earth, may be tied to forces shaping galaxies, shaping cosmic expansion, and shaping the long, unfolding story of everything that exists. We ended our last stretch of time by looking upward and outward, toward the cosmos itself, wondering how this same quiet vacuum energy might connect to the shape and history of the universe. Let's continue in that direction now, moving carefully from the language of the laboratory toward the language of the stars. Throughout tonight's exploration, we have circled back again and again to a single, quietly radical idea. The vacuum is not empty in any simple sense. And so it's worth pausing here to state that idea plainly, in the way physicists themselves often describe it. The vacuum is often characterized as something packed full of energy, not a passive void, waiting silently for something else to happen within it, but an active, energetic foundation, humming quietly beneath everything else that exists. This description may sound almost poetic, and in its own way, it is. But it also reflects something mathematically precise, drawn directly from decades of careful theoretical work, rather than simply metaphor or speculation. This energy is considered so real, so physically consequential, that researchers have begun designing experiments meant to reveal its influence in ways that go beyond what we've already discussed tonight. In quantum theory, vacuum energy is treated with enough seriousness that scientists are working to design experiments capable of showing it can slow light down, and even deflect it slightly from its ordinary path. Light, so often treated as the fastest and most unshakable messenger in the universe, may in fact be subtly influenced by the very vacuum it travels through, nudged, however faintly, by the quiet structure hidden within apparent emptiness. This possibility opens a fascinating door. If the vacuum can influence light's speed, and perhaps even its direction, then its effects may reach further than the more delicate laboratory measurements we explored earlier. the vacuum may influence light in ways that extend beyond simple propagation, suggesting that empty space itself is capable of altering optical behavior in ways physicists are only beginning to map out with precision. It's a profound thought to sit with quietly for a moment. The darkness between stars, the seemingly featureless stretch of space that starlight crosses to reach us, may not be quite as neutral a passage as it appears. It may be shaping, ever so slightly, the very light we look up and see. This idea connects naturally to another, even stranger concept explored within modern physics, the notion of quantum foam. At the smallest scales imaginable, far smaller than atoms, far smaller than anything our ordinary intuition can picture clearly, some physicists suggest that spacetime itself may not be smooth and continuous the way it appears to us in everyday life. Instead, it may be restless, irregular, bubbling gently with tiny fluctuations in its own underlying geometry. This is the essence of quantum foam, a picture of space and time, at their most fundamental level, appearing less like a calm, flat surface, and more like the fizzing, shifting texture of foam atop a wave, endlessly shifting in ways too small and too brief for us to observe directly, yet mathematically present within our deepest theories of reality. It's a striking image, and one that connects beautifully to something we touched on earlier in tonight's journey, the discovery that space itself is capable of physical motion. We spoke, a while ago, about gravitational waves, ripples predicted by Einstein's general relativity, eventually confirmed by careful, patient observation nearly a century later. And it's worth returning to that idea now, with a slightly different emphasis. Space itself can carry gravitational waves. This means the very geometry of empty space, the underlying shape of the universe's most fundamental fabric, is capable of rippling and changing, responding to the movement of massive objects across the cosmos. This challenges, once again, our everyday intuition about what emptiness should mean. We tend to imagine empty as synonymous with still. A space with nothing in it, we assume, should also be a space with nothing happening. And yet space can contain gravitational waves, meaning that even a region utterly devoid of matter may still physically oscillate, carrying real, measurable motion through its own structure. Emptiness, once again, does not imply stillness. Space can still support gravitational waves even when no matter is present at all, revealing, with quiet elegance, that a vacuum can possess something we might call dynamic geometry. Shape that shifts. Structure that moves. All without a single particle needed to set it in motion. There is one more place in the universe where these vacuum fluctuations take on particular significance, a place both extraordinarily distant, and yet deeply tied to some of the most fundamental questions physics has ever asked. Near the edges of black holes, in the region physicists refer to as the event horizon, vacuum fluctuations become especially important to a set of ideas connected to what is known as Hawking radiation. Near this boundary, the delicate flickering of particle-antiparticle pairs, the same fleeting activity we described earlier in far gentler laboratory settings, takes on extraordinary consequences. Under the right theoretical conditions, one particle from such a pair may fall inward, drawn permanently across the horizon, while its partner escapes outward, carrying away a small trace of energy from the black hole itself. Slowly, Gradually, over almost unimaginable stretches of time, this quiet process is thought to allow black holes to lose energy, and perhaps, eventually, to fade. It's a remarkable thought to hold in the stillness of this moment. The same fleeting particle pairs we described earlier, appearing and disappearing within the calm of an ordinary laboratory here on Earth, are thought to play a role in one of the most extreme and mysterious environments the universe contains. From the smallest, quietest corners of quantum experiments, to the crushing gravitational boundary of a collapsing star, the same underlying principle seems to echo throughout the cosmos, at every imaginable scale. And this brings us to perhaps the most sweeping idea of all, tying together everything we've gently explored across this long, unfolding journey tonight. These same vacuum fluctuations, appearing tiny and delicate within the careful, controlled conditions of a physics laboratory, are also thought to play a role in the large-scale structure of the universe itself. Somewhere in the earliest, most formative moments of cosmic history, tiny quantum fluctuations within the primordial vacuum are believed to have left their mark on the distribution of matter across space, subtle imperfections, stretched and amplified over billions of years, eventually growing into the vast cosmic web of galaxies, galaxy clusters, and empty voids that fill the observable universe today. The same quiet trembling we described earlier, flickering briefly within careful laboratory instruments, may be echoed on a scale large enough to shape the very architecture of everything that exists. And from here, we arrive at one final, almost dizzying possibility, one that some physicists have seriously proposed as a genuine scientific hypothesis, rather than simple speculation. The universe itself, in some theories, is thought to have arisen from a vacuum fluctuation. A stretch of nothingness, not unlike the quiet, restless emptiness we have been exploring throughout tonight's journey, briefly giving rise to something, expanding, growing, and eventually becoming everything we now see spread across the night sky above you. If this idea holds any truth, then the vacuum is not simply a backdrop against which the universe unfolds. It may be the very origin from which the universe itself first emerged, a quiet trembling, once, long ago, that never quite settled back down. Rest here for a moment, in that thought, as our journey continues gently onward. Everything above you, every star, every distant galaxy, every quiet stretch of darkness between them, may trace its beginning back to nothing more than a fleeting, quantum flicker within the vacuum itself. And it is with that vast, quiet thought that we'll carry ourselves forward, into the next stretch of facts still waiting ahead. We closed our last stretch of time with the thought that the universe itself may have first stirred into being from nothing more than a quiet vacuum fluctuation. It's a vast idea to rest with, and it leads us naturally into some of the largest and most unresolved questions in all of modern physics. Questions not just about where the universe began, but about where it may eventually be headed. Some modern theories connect the vacuum's quiet behavior to these larger cosmic questions directly. They explore how the vacuum might relate to the universe's ongoing expansion, and even to a strange and unsettling possibility known as vacuum decay, the idea that the vacuum we currently exist within may not be the lowest, most stable energy state available to the universe, but rather a kind of temporary resting place, one that could, in principle, shift to an even lower state at some unknown point in the future. We will return to this particular idea in a little more detail shortly. For now, it's enough to notice how far these questions reach. What began as a quiet exploration of empty space, here on the scale of laboratories and careful instruments, gradually extends outward until it touches the very fate of everything. Because of this reach, the vacuum has come to be described by many physicists as a leading candidate source for the universe's large-scale behavior, connected not only to how everything began, but potentially to how everything might end as well. It's a striking symmetry to sit with. The same subtle structure we've been tracing all evening, flickering quietly beneath what once seemed like simple nothingness, may hold within it clues to both the origin and the eventual destiny of the cosmos entire. This is part of why, in the field of cosmology, understanding the vacuum more completely has become such an important pursuit. A deeper grasp of what the vacuum truly is, and how it behaves, may be essential for explaining both the beginning and the end of the universe. Two questions that could not feel further apart in scale, the birth of everything, and the conclusion of everything, may, in the end, share the same underlying answer, hidden somewhere within the quiet architecture of empty space. This is also why the vacuum is so often discussed as a kind of bridge, connecting two of the most successful yet strangely incompatible frameworks in all of physics. On one side stands quantum theory, extraordinarily precise in describing the smallest scales of existence. On the other stands the large-scale expansion of the cosmos, described with remarkable success by general relativity. The vacuum sits quietly between them, offering, at least in principle, a shared foundation upon which both frameworks might eventually be unified. And nowhere does this bridging role become more apparent, or more challenging, than in what physicists call the cosmological constant problem. To understand this problem, it helps to slow down and consider two very different ways of estimating the same underlying quantity, the amount of energy contained within empty space itself. From one direction, quantum field theory offers its own prediction. And this prediction is almost unbelievably large. The energy predicted for empty space by quantum field theory is vastly larger than what the universe actually seems to allow, based on everything astronomers have observed about how the cosmos expands and behaves. This mismatch is not a small discrepancy, easily explained away with minor adjustments. It is often considered one of the largest and most striking numerical disagreements in the entire history of physics. This gap between prediction and observation has become known, quite directly, as the vacuum energy problem, and it stands today as one of the most significant unsolved puzzles in all of modern science. It connects closely to two of the biggest open questions currently facing cosmologists. The nature of dark energy, that mysterious pressure we touched upon earlier, believed to be driving the universe's ongoing expansion. And the broader question of how that expansion itself has unfolded, and continues to unfold, across billions of years of cosmic history. Part of what makes this puzzle so striking lies in the numbers themselves. When physicists attempt certain calculations of vacuum energy directly from quantum theory, without applying any additional adjustments or careful interpretation, the results can appear to grow infinitely large. Some calculations of vacuum energy in quantum theory produce infinite values before what is known as a physical cutoff, or a more careful theoretical interpretation, is applied to bring the numbers back into a workable, finite range. This alone hints at just how delicate and unusual this area of physics remains, a place where our best mathematical tools, applied too directly, seem to overreach the bounds of what nature itself appears willing to allow. Once physicists apply these necessary adjustments, they arrive at a theoretical estimate for vacuum energy, one that remains, even after careful refinement, astonishingly large. And this is where astronomy enters the conversation, offering a very different number entirely. By observing the actual rate at which the universe is expanding, cosmologists have arrived at their own estimate for how much vacuum energy the cosmos appears to contain. And this observed value, drawn directly from careful measurements of distant galaxies and the pace of cosmic expansion, turns out to be extraordinarily small, especially when set beside the raw estimate quantum theory initially produces. The scale of this disagreement is genuinely difficult to put into ordinary words. The enormous mismatch between these two very different pictures, one theoretical, one observational, forms the very heart of the cosmological constant problem. It is not simply that the two numbers disagree. It is that they disagree by a staggering, almost unimaginable margin, large enough that physicists across the world consider resolving this gap to be one of the most important unfinished tasks remaining in fundamental physics. Somewhere within this gap lies a clue we have not yet fully understood, a missing piece of reasoning, a hidden principle, or perhaps an entirely new layer of physics not yet discovered, that would allow these two very different estimates to finally align. Faced with a puzzle this deep, physicists have continued searching for new ways to approach it, and some of the more recent theoretical work has begun exploring an intriguing possibility. Rather than treating vacuum energy as a fixed, unchanging quantity, frozen in place for all of cosmic history, some researchers have proposed that vacuum energy might instead behave as something capable of gradual change. This idea treats vacuum energy as a quantity that can, in a sense, run alongside the universe's expansion, shifting gradually over enormous stretches of cosmic time rather than remaining perfectly constant from the earliest moments of existence through to today. It's a subtle shift in thinking, but a meaningful one. If vacuum energy is not entirely fixed, then perhaps some of the tension at the heart of the cosmological constant problem could ease, at least in part, once this evolving behavior is properly understood and incorporated into our broader picture of cosmic history. This remains an active and unsettled area of research, one without a final answer yet in hand. But it offers a reminder of something we have returned to again and again throughout tonight's long, quiet journey. The vacuum, in nearly every context where physicists have examined it closely, resists simple, static description. It shifts. It responds. It reveals new layers of behavior each time our tools become precise enough to look a little closer. As we drift onward from here, carrying this image of a vacuum energy that may not be entirely fixed, but capable of subtle change across the vast unfolding history of the cosmos, we'll begin turning our attention towards some of the broader implications this uncertainty carries, what it might mean for the universe's distant future, and how physicists continue searching, patiently and carefully, for a more complete understanding of the emptiness that surrounds and connects everything. Let's continue gently from where we left off, with this idea that vacuum energy may not be entirely fixed, but capable of subtle change across the long history of the cosmos. It's worth spending a little more time here, exploring exactly how physicists have tried to describe this kind of change mathematically, because the details reveal something quietly beautiful about how deeply connected the vacuum is to the universe's own unfolding rhythm. In what researchers call running vacuum models, the vacuum energy is not treated as a fixed backdrop, unaffected by everything happening around it. Instead, it is described as something that depends on the Hubble rate, a quantity that measures how quickly the universe is currently expanding, along with how that rate itself is changing over time. In other words, the vacuum's energy becomes tied directly to the universe's own expansion history, rising and falling, ever so gently, in step with the broader rhythm of cosmic growth. It's a striking picture. The emptiness surrounding every star and galaxy, subtly listening and responding to the pace of the universe's own unfolding. This idea did not emerge from nowhere. Such models draw their motivation from a deeper and more technical corner of theoretical physics, tied to what is known as renormalization, a set of mathematical techniques developed within quantum field theory to make sense of quantities that might otherwise grow unmanageably large, or even infinite, much like the vacuum energy calculations we discussed a little earlier. When these techniques are extended into the curved, dynamic spacetime described by general relativity, rather than the flatter, simpler space often assumed in basic quantum theory, they naturally suggest that vacuum energy could evolve gradually alongside the universe's own expanding geometry. It is, in a sense, an attempt to bring two of physics' most successful frameworks into closer conversation with one another, allowing the deep quantum understanding of the vacuum to remain consistent even as the universe itself stretches and grows around it. Within these more detailed models, the vacuum's energy is not shaped by a single, uniform influence. It can receive quantum corrections from a wide range of underlying particles, drawn from two broad families that populate the universe at its most fundamental level. Bosons, the category of particles responsible for carrying forces, and fermions, the category that includes the particles making up ordinary matter. Both contribute their own quiet influence to the vacuum's overall behavior, layering subtle corrections atop one another as physicists work to build an increasingly complete picture of how empty space truly behaves. This complexity leads to another subtle but meaningful possibility. In simpler cosmological models, vacuum energy is often treated as having what is called an equation of state equal to -1, a mathematical way of describing how its pressure relates to its energy density, in the cleanest and most idealized form. But some of the more detailed calculations emerging from these running vacuum models suggest that this value may not be perfectly fixed after all. The vacuum's true equation of state may deviate slightly from that ideal value of -1, hinting at a richer, more textured behavior than the simplest cosmological models originally assumed. It's a small deviation in mathematical terms, but one that could carry meaningful consequences for how we understand the universe's long-term expansion. Some researchers have taken this line of thinking even further, exploring more intricate mathematical terms that might describe the vacuum's evolution across cosmic history. Among these are higher-order terms, including ones tied to a quantity called H6, referring to a more complex relationship involving the Hubble rate raised to a higher power. These terms have been proposed as possible ingredients within the earliest moments of the universe, particularly during a period known as inflation, an extraordinarily brief but explosive phase of expansion believed to have occurred just after the universe's birth, stretching space outward at a pace almost impossible to fully picture. If vacuum energy carried these more complex terms during that early era, it may have played a direct role in driving that dramatic expansion, shaping the very earliest structure of everything that would eventually follow. It's worth noting, too, why physicists continue pursuing these more elaborate dynamical vacuum models in the first place, rather than resting comfortably with simpler explanations. Certain versions of these models are studied specifically because they may help address a handful of quiet tensions that have emerged within standard cosmology, small but persistent disagreements between different methods of measuring the universe's expansion rate, discrepancies that have puzzled researchers for some time now. A vacuum energy capable of subtle change over cosmic history offers one promising avenue for potentially resolving these tensions, weaving together observations that might otherwise seem difficult to reconcile. Having spent this time exploring the vacuum's relationship to the grand, sweeping scale of cosmic expansion, let's shift our attention now towards something a little closer to home. The vacuum as it appears within the forces that hold ordinary matter together. In particular, within a branch of physics known as quantum chromodynamics, which describes the strong force responsible for binding together the particles found deep inside atomic nuclei. Here, too, the vacuum reveals itself as anything but simple or featureless. In quantum chromodynamics, the vacuum can contain quark-antiquark activity, a quiet flickering of particle pairs, similar in spirit to the vacuum fluctuations we explored earlier, but tied specifically to the strong force and the particles it governs. This activity is not a minor background detail. It plays a meaningful role in shaping how larger particles are able to form in the first place, influencing the very building blocks from which protons, neutrons, and the deeper structure of matter eventually take shape. This leads to a genuinely surprising realization, one that gently reshapes how we think about the mass of everything around us. Earlier in tonight's journey, we spoke about the Higgs field, and its important role in giving fundamental particles their mass. It would be reasonable to assume that this single mechanism accounts for most of the weight and substance found in ordinary matter. But the strong force vacuum appears to contribute a great deal as well, and in fact, may contribute significantly to the mass of ordinary matter, even though most of that mass does not come directly from the Higgs mechanism at all. Instead, much of the mass we experience in everyday objects, in your own body, in the ground beneath wherever you happen to be resting tonight, may trace back to the restless, energetic activity occurring within this deeper, strong force vacuum, rather than from the Higgs field alone. It's a wonderfully humbling thought. So much of what feels solid and substantial about the physical world may owe its weight not to a single, elegant field quietly assigning mass to particles, but to the complex, churning activity of a vacuum most of us have never had reason to think about at all. And this brings us, gently, to one of the more forward-looking ideas we'll touch upon tonight, a question some physicists are only beginning to explore in careful detail. If the vacuum can influence mass, and shape the structure of matter at such a fundamental level, could it perhaps be responsible for even more? Some physicists now explore whether visible matter itself, the atoms, the particles, the very substance of everything we can see and touch, could emerge from deeper correlations occurring within the quantum vacuum. Rather than treating matter and vacuum as separate categories, entirely distinct from one another, this line of research considers the possibility that matter might, in some deep sense, be a quiet expression of the vacuum's own underlying structure. This remains an active and evolving area of study, but recent experimental work has begun offering intriguing hints in this direction. New detector work has reported patterns known as spin correlations, subtle relationships in how certain particle properties align with one another, observed under carefully controlled conditions. These correlation patterns may offer valuable insight into how matter can arise from what appears, on the surface, to be nothing at all. It is early evidence, cautiously interpreted, and far from a settled conclusion. But it points toward a possibility that feels almost poetic to sit within this quiet moment. That the solid, tangible matter filling the universe, and the vast, seemingly empty vacuum surrounding it, may not be two separate things after all, but two expressions of the very same underlying reality, connected far more intimately than our everyday senses could ever suggest. As we continue forward from here, we'll carry this thought gently along with us, that the boundary between something and nothing may be far softer, and far more porous, than it first appears. And it's with that quiet, open question resting in mind that we'll move ahead into the next stretch of facts still waiting to unfold. We left off with a thought worth carrying forward carefully, that matter and vacuum might not be two separate things, but two expressions of the same deeper reality. As our exploration continues, we'll see this idea taken even further, into some of the more recent and more ambitious research shaping how physicists think about empty space today. For much of tonight's journey, we've traced the vacuum's presence through its effects, through forces, through subtle shifts in energy, through fleeting particles rising and falling in the quiet dark. But there is a newer, complementary approach emerging within physics, one that turns to a different kind of evidence altogether. The vacuum is increasingly treated as something that can be studied through particle correlation measurements, not only through force effects. Rather than asking only how the vacuum pushes or pulls on nearby objects, researchers have begun asking a subtler question. How do particles, once they emerge from high-energy processes, carry relationships with one another that trace back to the vacuum they came from? It's a shift in perspective, from watching what the vacuum does, to listening for what the vacuum remembers. This shift has opened the door to some genuinely striking theoretical proposals. One modern line of research suggests something quietly profound, that the wave function itself, the mathematical object at the very heart of quantum mechanics, describing the probabilities and behaviors of particles, may actually be a property of the vacuum, rather than simply a description layered on top of particles that already exist independently. For most of the history of quantum theory, the wave function has been treated as a kind of tool, a mathematical description of a particle's possible states, calculated and applied from the outside. But this newer perspective suggests something different. That the wave function may not merely describe particles moving through the vacuum. It may, in some deep sense, belong to the vacuum itself, an expression of the vacuum's own underlying nature, rather than something separate imposed upon it. If this idea holds true, it carries a fascinating implication. It suggests that the vacuum may behave, in certain respects, like a physical medium, one capable of carrying waves, much the way water carries ripples, or air carries sound. This is a very different image from the vacuum we might have imagined at the very beginning of tonight's journey, not merely a stage on which particles perform, and not merely a source of fleeting fluctuations, but something closer to a medium in its own right, with the capacity to carry, shape, and sustain wave-like behavior across its structure. Building on this idea, some researchers have proposed something even more specific. Rather than viewing the vacuum as a simple, passive backdrop, one modern proposal suggests the vacuum may be a nonlinear, self-consistent medium. This is a fairly technical description, but its meaning is worth sitting with quietly for a moment. A linear medium behaves predictably and independently, simple causes producing simple, proportional effects. A nonlinear medium is far more intricate. Its behavior can depend on its own internal state, folding back upon itself in ways that resist easy prediction from the outside. To describe the vacuum this way is to suggest that it is not simply reacting to whatever passes through it, but is instead behaving according to its own deep, internally consistent structure, a structure complex enough to shape, and be shaped by, the very things moving within it. Under this view, much of what we explored earlier in tonight's journey takes on a slightly different meaning. The vacuum fluctuations we described, the fleeting virtual particles rising briefly into existence before dissolving again, are reframed not as the deepest layer of vacuum behavior, but as surface-level descriptions of something even more fundamental happening underneath. In this view, vacuum fluctuations and virtual particles are treated as the visible ripples atop a much deeper current, useful and accurate descriptions at their own level, but not necessarily the final word on what the vacuum truly is, at its most foundational core. This deeper, more intricate picture of the vacuum has become closely tied to one of the more pressing questions in modern particle physics. Quantum vacuum research is now connected directly to the question of how visible matter emerges from high-energy particle collisions, the kind of extraordinarily energetic smash-ups produced inside massive particle accelerators, where particles are hurled toward one another at speeds approaching that of light, and the resulting collisions are studied in extraordinary detail. These collisions offer physicists a rare and valuable window, a chance to peer, however briefly, into conditions extreme enough to reveal subtle traces of the vacuum's deeper structure, ordinarily hidden from view under gentler, everyday conditions. Some of the most interesting recent findings in this area draw on the same idea we touched upon toward the end of our last stretch of exploration. New experiments have used spin correlations in outgoing particles, the subtle way certain particle properties align with one another after a collision, as clues pointing toward the underlying nature of the vacuum state itself. It's a delicate, indirect kind of evidence. Physicists cannot observe the vacuum directly in these experiments. But by studying how emerging particles relate to one another, how their properties correlate in patterns too precise and too consistent to be coincidence, researchers can begin piecing together a picture of the deeper vacuum dynamics that shaped their creation. This approach reflects a broader idea gaining traction within the field. Some researchers argue that the vacuum may carry information Information that can be inferred not only from direct forces, of the kind we explored earlier in tonight's journey, but from these more subtle particle correlations as well. In this sense, the vacuum begins to resemble something almost like a quiet archive, not actively remembering in any conscious sense, but structured deeply enough that its own nature leaves a consistent, traceable imprint on whatever emerges from within it. This has become a genuine and active focus of ongoing research. Recent work in the field has concentrated specifically on whether the vacuum can be probed through detector signatures gathered from these energetic smash-ups, carefully analyzing the aftermath of high-energy collisions, searching for patterns subtle enough to reveal something meaningful about the vacuum's underlying structure, hidden just beneath the visible debris of the collision itself. Taken together, these threads point toward a description of the vacuum that feels, in some ways, like a natural culmination of everything we've explored across tonight's long, unfolding journey. Researchers have come to describe the vacuum as a medium, one whose fluctuations, whose quiet internal structure, whose deep and restless nature, can, in principle, be studied through the properties of the particles it produces. Not simply through the forces it exerts. Not simply through the energy it carries. But through the particles themselves, understood as quiet messengers, carrying traces of the vacuum's deeper nature outward into the world where careful instruments, and careful minds, are waiting to listen. It's a beautiful thought to rest with as we approach the later portion of tonight's exploration. The vacuum, once dismissed as simple nothingness, has revealed itself, layer by layer, as something closer to a hidden architecture underlying all of reality. A medium capable of carrying waves. A structure capable of shaping mass. A quiet source, some theories suggest, from which matter itself may ultimately emerge. And now, a system whose secrets may be legible, if only we learn to read them carefully enough, in the particles it leaves behind. As we move forward into the next stretch of facts, we'll begin drawing these many threads a little closer together, gathering the different perspectives we've gathered throughout tonight's journey, and preparing, gently, for the broader reflections that lie ahead as our exploration of empty space continues to unfold. We left off with the idea that the vacuum might be legible, its deeper structure written quietly into the particles it produces, waiting for careful instruments to read what it has to say. Let's continue there now, moving into some of the most recent findings in this area, before gathering everything we've explored tonight into a final, quiet resting point. New collider studies have begun to suggest something remarkable about the particles emerging from these high-energy collisions. Some of these particles appear to preserve a spin signature, a subtle trace, inherited from the quark pairs born briefly within the vacuum during the collision itself. It's a delicate thread to follow, but a meaningful one. If particles created in these violent, energetic events carry forward a signature tied to their vacuum origins, then the vacuum is not simply the stage where these particles are born. It leaves its own quiet fingerprint on what it creates, a fingerprint that persists long enough, and clearly enough, for physicists to detect it afterward. This has made the vacuum useful in an unexpected way, not simply as a subject of study in its own right, but as a source of clues about a much older and more difficult question. How does mass actually arise within the strong interaction, the force responsible for binding together the smallest building blocks of atomic matter? We touched on this earlier in tonight's journey, when we explored how the strong force vacuum contributes significantly to the mass of ordinary matter. These newer collider studies offer a promising path toward understanding that contribution more precisely, using the vacuum's own quiet signature as a guide. Among the more striking developments in this area, a result reported in 2026 from researchers working at Brookhaven offered evidence that particles emerging from high-energy collisions retain a signature tied to the short-lived virtual particles associated with the quantum vacuum. This finding, still relatively recent within the broader arc of this research, carries real significance. It suggests, with growing confidence, that the vacuum may leave a detectable imprint on real matter, matter that exists, stable and measurable, well beyond the fleeting instant of the collision that created it. Not merely a passing trace, gone as quickly as the virtual particles themselves, but something lasting enough to be captured, studied, and confirmed. It's worth pausing to consider just how carefully this kind of finding must be verified before physicists are willing to trust it. In this particular area of research, recent evidence has, in some analyses, reached what scientists describe as the 3 to 4 sigma level, a measure of statistical confidence indicating that a result is very unlikely to have occurred purely by chance. This is not yet the very highest threshold physicists typically require before declaring a discovery fully confirmed. But it represents a meaningful and encouraging level of confidence, strong enough to suggest that this connection between the vacuum and the particles it produces is a real, physical relationship, rather than a statistical coincidence. Findings like these naturally invite bigger, more speculative questions, the kind that tend to capture public imagination, even when the underlying science remains cautious and incomplete. If the vacuum truly carries energy, structure, and even detectable influence over the matter it helps create, could that energy ever be put to practical use? Some recent theoretical claims have proposed that vacuum energy might, in principle, be extracted in practical ways. It's an intriguing idea, one that sounds almost like something drawn from imaginative fiction rather than careful physics. But it's important to hold this possibility with appropriate care. This idea remains highly speculative, resting far outside the more established and well-supported areas of vacuum research we've spent tonight exploring together. This naturally leads to a very reasonable question, one physicists are asked often, and one worth answering clearly and honestly here. Could vacuum energy ever become a usable source of power, something we might one day draw upon, the way we draw energy from sunlight, or wind, or the careful splitting of atoms? Physicists are indeed exploring whether vacuum energy could ever be harnessed in some meaningful way. But our current understanding offers a clear and fairly firm answer. The vacuum cannot be used as a free source of energy. Whatever richness and activity we've discovered within it throughout tonight's journey, it is not a hidden well from which limitless power might one day be drawn. The reason for this comes back to an idea we explored earlier, quietly but firmly. The vacuum represents the lowest energy state available to the universe's fields, its ground state, the calmest possible configuration those fields can settle into. And because it already occupies that lowest possible state, there is no lower state remaining, nowhere further down for that energy to fall, and therefore no way to draw net energy out of it. you cannot pour water downhill from the very bottom of a valley. And in much the same way, you cannot extract usable energy from a system already resting at its lowest possible point. The vacuum's energy is real, and it is vast in its own way. But it is not available to us, not in the way sunlight or fuel might be. It remains, instead, a quiet, foundational feature of reality, present everywhere, influencing everything, and yet fundamentally out of reach as any kind of practical resource. And so, after so many hours spent exploring this strange and quietly restless corner of physics, we arrive at a description that feels like a fitting way to gather everything together. Some popular explanations now describe the vacuum as the most active place in the universe, not because it churns with visible motion the way a storm or a star might, but because it never fully settles into complete stillness. Even at its calmest, even stripped of every particle, even cooled to the coldest temperature the universe allows, something within it continues to stir, gently and endlessly, beneath the surface of what appears, to our eyes, and even to many of our instruments, as perfect silence. We began this journey many hours ago, looking upward into a sky that seemed, at first glance, defined mostly by darkness and distance. Empty space, stretching between one star and the next, felt like the simplest possible backdrop against which the universe's real drama unfolded. And yet, across everything we've explored together tonight, from ancient philosophy to modern particle colliders, from ether that never existed to gravitational waves that quietly do, that simple picture has been gently, patiently dismantled. We've seen the vacuum defined by physics as a precise, measurable state of low pressure, and also as something deeper, the calm, ground state hum of quantum fields, filling every corner of existence. We've seen it flicker with virtual particles, exert real force between metal plates, and shift the very energy levels of atoms. We've seen it stretch and ripple with gravitational waves, whisper near the edges of black holes, and perhaps, in its earliest fluctuation, give rise to the universe itself. We've followed it into the deepest questions of cosmology, into the mystery of dark energy, into the staggering unresolved gap of the cosmological constant problem. And we've followed it, most recently, into the debris of high-energy collisions, where its quiet signature may be written into the very particles that build the ordinary matter around us. Taken all together, the vacuum is increasingly seen by physicists not as an absence, but as something closer to a hidden foundation beneath reality itself, a foundation that may hold within it the key to understanding matter, and gravity, and the strange pressure of dark energy pushing our universe ever outward, and perhaps, one day, the universe's own ultimate fate, whatever quiet form that fate may take. What we once called nothing may turn out to be the thread connecting everything. So as you rest here now, in whatever dark and quiet room surrounds you, let this final thought settle gently alongside you into sleep. The space above you, and the space around you, and even the space within the smallest gaps between the atoms of your own body, is not empty in the way we once assumed. It is full, quietly, endlessly full, of fields, and fluctuations, and a soft, restless hum that never entirely fades. Somewhere in that hum may lie the origin of every star you've never seen, and the answer to questions physicists are only just beginning to ask. For now, there is nothing more to do than let that quiet hum carry you gently, the way it has carried the universe itself, from its faintest beginning into everything that followed. Rest well.